The basis of this video is predicated on a notion, and here's the notion. I was considering to myself, Eric Dollard has said that in order to generate so-called what we like to think of as free energy or over unity in a purely electrical system, he didn't say purely, but I'm qualifying it in order to demonstrate to you and I that there are contingencies when dealing with free energy. And so here's the contingency. If we're dealing with a strictly electrodynamic system, which is not what's in front of your face, actually, that's a poor example. What would be a good example? Caps and coils. If you recall, Eric Dollard's LMD module is analog computer in LMD mode. Is strictly caps and coils paired. Let's see. So here we have a coil and a cap, but it's only one of each. We need two of each. So let's see if I can find one that's a cap and a coil. Well, yeah, I have actually several. If we go into battery chargers, you know what I'm looking for is Songalani. I don't think it's House of Mirrors, but yeah, I didn't think so. How about improvements? No. Okay, analog switching. Here we go. External load. So here we have a circuit. We almost don't even have to turn on the switch to use this battery to get it started. It's a self-starter right off the aerial, the AM radio input. And it's regulated voltage, so we have this battery that's around 44 volts, and we want to charge it because we want to do a concept known as battery rotation, in which we discharge during 3 out of 5 phases of rotation. We charge during 1, we let it rest, and then we go through the discharge cycle of 3 phases again. And each of the discharge phases might be, as an example, just an arbitrary choice I made, 9.3 microseconds for each of these 3 discharge phases, and then 0.95 microseconds for the charging phase, and then 0.05 microseconds for the resting phase. And by rotating batteries, you could have an over-unity situation. And here we see that the battery is getting charged with negative 5.82 kiloamps, and the voltage being applied is 56.66 negative volts, which is good. It's slightly more than 44. So it's a slight over voltage, which will ensure that it be charged. Now the aerial, the AM source, is a lot of waste, 320.89 kiloamps, and we used no energy to get this thing started coming from the battery. It all came from the aerial. So this is a pretty good example of a situation that has 2 caps and the 2 coils on this transformer, creating a LMD module with a lot of other things thrown in to boost this thing along, such as spark gaps, rated for neon bulb situation, whether or not that's realistic, analog switches to toggle back and forth, some mild coils to act as branch circuits to take the load off of the LMD module, and then this other arrangement up here that actually has to do with the battery charging, which involves the use of 2 diodes, some resistors, and this coil here, which has a tremendous amount of voltage building up on it, It's so huge, it kind of makes you shudder to think that you would want to get into teravolts. But see, this is exactly what Eric Dollard warned us, that if you want to create any over unity in a strictly electrodynamic system, and this isn't strictly because we've got analog switches going on here, but it's pretty close, then you have to expect 500 kVA minimum production rating. Something akin to a substation within the power grid. And that's what's happening here. This coil here is teravolts. And the amperage is kiloamps, okay, but it's teravolts. And the aerial is 300 plus kiloamps. Just to get, it looks like 55 volts and 5 kiloamps across this battery to charge it. Now these are spikes, and so that's why I think maybe we can get away with 5 kiloamp spikes, because they're just spikes. It's not continuous AC or continuous DC, whatever. Well, in this battery, of course, it would be DC. So it's not continuous DC that would chew out the battery and, you know, drive the poor thing wild before it died or exploded. It's spikes. And so there are these fraction second rests between the spikes, unless they're really on top of each other. But still, they're spikes. And so maybe we could get away with it. Maybe. But this poor inductor over here, well, that's spikes too. In fact, this whole thing runs on spikes. And these spikes are unidirectional DC impulses. And so this is a almost purely solid-state mechanism. It's still some mechanical involved, but it's strictly electrical. There is nothing, well, it's almost strictly. It's almost no kinetic action taking place here. And there's certainly nothing thermal going on here. Now, the reason why I say this is because if we take a look at spontaneous combustion, and my theory is that spontaneous combustion is first an electrical phenomenon before it becomes a thermal or oxidative phenomenon, thermal resulting from oxidative. And because we look at it, the body is doing it off of extremely low voltage levels and current levels, and yet it's able to fry the poor person, body parts, you know, disappearing, totally being consumed by flame, and you're left with maybe a stump of a foot that failed to burn, or just wasn't ignited or whatever. Maybe the surge, the electrical surge, was not happening in the foot, but it was happening everywhere else that got burned and totally consumed. So, and also when we know but that electricity can appear and disappear because it can be synthesized or decomposed in various areas of a circuit, what if it's a bidirectional relationship between oxidation and electricity, such that once the oxidation goes, it feeds by feedback. It creates a feedback to the electrical, boosting that even more, and doing a conversion of the combustion into electrical, which means if we do the conversion, if the body does the conversion, then the body could disappear, parts of it, because it was converted into an electrical phenomenon after the electrical already converted into the oxidative phenomenon. So if there's a back and forth, two-directional, bidirectional conversion taking place in a spontaneous combustion situation. In any case, it's very highly efficient because it's making use of chemistry, oxidative chemistry, at the very least, if not also reductive chemistry, but oxidative at the very least in conjunction with electrodynamics. And that's when you raise your efficiency levels so high that the kind of grid, the power grid that we have employing thousands of volts would never be necessary. The whole thing would get scaled down, and it's no small wonder that Tesla was able to come up with a method for his so-called Pierce Arrow experiment of 1931. Now, let's close this. So now we go to Tesla's special generator, in which we have compressed air moving this piston back and forth, designed in such a way that the periodicity of the reciprocation of this piston is constant no matter what the pressure of the compressed air is, or for that matter, what is the pressure of the atmosphere surrounding it. And the only way I can estimate why that is the case is because it functions, the piston's reciprocating action functions no different than a reed in a wind instrument, such as a clarinet, let's say, as opposed to a trumpet, which if you vary, or a flute, if you vary the pressure coming out of your mouth, you will vary the pitch in addition to the fingering. And this is where, you know, I'm no musician, all right? But I took flute lessons from a jazz flautist by the name of Sam Most, and it gave me the background, I guess, I needed to be able to cognize why this is a constant periodicity. Because it's not stated in Thomas Comerford Martin's treatise at SpecGen pages, this link right here. You know, it's not stated in this link. It's a shortcut, obviously. So, wait a minute. Here we go. So this goes to archive.org, and I just transcribed a portion, the last chapter, chapter 63, of Thomas Comerford Martin's text, in which he was there at the demonstration. He saw it happen, and Tesla talked about it. And then, of course, we have William Line, who also talks about it. Where's that? Oh, dear, dear, dear. Lynn Author, here we go. Or is it this one? What's this? Well, let's see. I don't know where this goes to. Oh, I see. This is chapter 8 of William Lyne's book, Pentagon Aliens. So that's not what I had in mind. That actually he's basically talking, you know, okay. It's a good link, but that's not what I wanted to bring to your attention. So I think this is the link. Line Author here. Yeah, this is it. So he's got a website, and he's only got one blog on it. And he does spend some time talking about Tesla's special generator in here, and it's pretty cool. Aaron Murakami helped him set up the website. Anyway, so that's the link I want you to focus on, I believe. Yeah, and then there's the others, but they're not too important. Anyway, so in researching this, I came to that conclusion that that's how the piston works. Now, the thing to try to figure out here, though, is how do these coils work in conjunction with each other? These H coils and the M coils. This is an M coil here and here. So, when I did this circuit, let's wait a little bit. Well, no. When I did this circuit, I made various presumptions. Now, this is one of two circuits. This is pre-charged. So, the values of voltage and amperage on these two inductors are pretty constant because I've already gotten them up to that point. You know, there's another version to this circuit. Where is it? Complex manual switching. I keep forgetting where I put these things. Oh, it's not that one. Oh, no. Oh, here we go. See, now this one, it's actually a cold start that we start from it, and the shortcut here is add induct. and we get it going, and it slowly builds to whatever value you want it to build to. And then to freeze it at that point, you raise the inductance on this pair of coils on this transformer here. Now it's still rising, but when it rises up to a certain point, maybe let's speed it up a little. So this circuit is not pre-charged. It's a cold start. And this is 200 microsecond time step, so... Okay, so no, it's not there yet. It's still pretty slow. See, I was being conservative because I didn't want it to run too fast. Build too fast, I mean. So it's still picovolts, picoamps. Nano. Let's get it up to kilo, if we can. But let's see if I can. Micro. Milli. Amps. Kiloamps. Okay. Now this transformer up here starts out at 100 kilohenries. So we change it to 100 exa or ectahenries. Now notice the coupling coefficient, 1.01. Now the problem is the point of this video is trying to figure out, what does this mean, you know? And my guess is aluminum. That the core of this transformer is aluminum. That means that these two coils are the H coils. And when you have an inductance... Oh, it's backwards. It's the other way around that I thought it would be. Whoops. Uh-oh. Oh dear. Now my idea is shot in the water. I thought this was the one with the pico henries. But it's not. I'll be damned. Okay, so now I'm going to have to run with this. Okay, so this would not be the aluminum one. This would be the one in which so this would be the M coils, and in which the horseshoe whoops. Okay. Oh no, wrong one. Alright, now where'd I get that? I keep doing the wrong one. All right. Okay, so these horseshoe cores, these laminate cores of the M coils, they're bolted to the floor of an electro U-boat that's been specially outfitted to run this device. And so it's incorporating the massive hull of the electro U-boat by way of magnetic coupling as an extension of the M coils core, the core of the M coils. So, so when we come in here and say, well, that's 1.01, so that I would have to assume then, different than what I was expecting, that this is actually the iron core of the M coils. And now that I have it increased, it will iron out to a level, as you can see, much lower than kiloamps. If we can wait for it to iron itself out here. It drops, but not down to 0. Drops down to its plateau of pretty close to what my pre-charged version is. 200 amps and 142 volts. How about that? So that's how you do it. You go up to kiloamps. So now this will run at a pretty constant rate because the amount of inductance is very high, but it's still 1.01 coupling coefficient. Now if we come down to here that we didn't change at all, we see it's got 1 picohenry, and the coupling coefficient is huge. So now we've got a real problem. How does that equate to... I can't do that. To... oh, it's the wrong one anyway. How does that equate to these H coils? Because it looks like we have a non-aluminum coupling here between the 2 aluminum rods here and here. You know, this could be iron. Now that means there's going to be a galvanic response between them, and so is this how you boost the coupling coefficient? By having 2 aluminum rods of 2 separate coils with 2 counter-wound coils here that are have an iron insert here between them? Is that how you get a... what was that ridiculous sum? I don't know how many zeros that was. Oh my god. Let's see. 1, 2, 3, 1, 2, 3, 1, 2, 3. So, 100,000, 100 million. 100 million coupling coefficient. How in the world do you get that? Well, is this how? 2 aluminum rods, and I guess this is a galvanized iron pipe between them, or maybe it's plastic. I don't know. We don't know. I don't know what material this is. I don't know if they had plastic or PVC plumbing in those days. You know, back in 1894, which is when Thomas Comerford Martin went to the lecture. So that's a pretty long time ago. So this would have to be an iron pipe. I would have to assume that. Could be brass. Okay, it could be brass. So it's either brass or iron or steel, whatever. Let's say iron. I'm going to guess it's probably brass. In all likelihood, that's probably what it is. So if we got brass or copper, probably brass, in between 2 aluminum rods, that's very interesting, because those are the 3 materials of the phrase Tesla's trimetal generator. And that's the other title or name given to this Tesla special generator. He called it his special generator, but William Line, or, you know, people on the internet call it the trimetal generator. And apparently there's a solid state version or a scaled down version. And usually once you know how something works mechanically, you can convert it into a solid state version. But have you really made it solid state? You know, because maybe not. Maybe you just scaled it down and there's still kinetic motion built into it. Be that as it may, if this is a brass or copper pipe in between 2 aluminum rods, and the aluminum rods are in their coils, their copper coils are surrounded by a magnetic field on either side of them coming from laminate iron sheets, composing 2 halves of 2 horseshoe magnets that are brought together to create a circular magnetic pathway. Maybe there's something to that raises the inductance values of these teeny weeny little coils to a value of 100,000 henries, despite the fact they're so teeny. And if that's true, then that would explain the overunity right in here, because the inductance is so high. Here, well, oh no, wait a second. No, the simulation has this generating a lot of inductance. Oh, this is why it's so confusing. Yeah, it would make more sense that this would be the M coils. Right. I mean, oh, God. Yeah, this can't possibly be the M coil. Yet how can you get a coupling coefficient that is so huge? That's the magic of possibly of this arrangement, this shaft arrangement that's made of what looks like two different materials of composition. Aluminum here and maybe copper or brass here. That's the best I can come up with in this video. So the inductance is low, and we would expect it to be because these are teensy little coils, but the coupling coefficient is massive. And when you look at the equations, such as I've done trying to monkey with Paul Falstad's software, it's a different way of, it's another way around, kind of like a back end run, like an end run, or what do we call it? A workaround solution to how do you boost inductance. Well, you boost the coupling coefficient instead, and then alternate between those two different opposing characteristics, because the characteristic is not just one quality but a pair of qualities, namely the inductance and the coupling coefficient. The ratio is 1 to 1, so they're both the same in both cases. But, you know, because they're matching coils. These counterwound coils have the exact same number of windings on one aluminum rod, as opposed to, you know, comparison to each other, the two coils, but also by comparison to the other pair of coils on the other side here. But also these two M coils would have to have the same number of windings as well to maintain a 1 to 1 correspondence. And the reason why I think, let's just take this one for example, the M coils. Here we have a magnetic circuit that's kind of circular in a sense. Even though it's broken in the middle, it's still somewhat circular when the coils, the H coils, are not interrupting the magnetic flow. You know, when they're in here, they're interrupting it, but when they start to slide out, they don't interrupt it. And so right now, it's circulating all the way around. So it's a total toroidal situation. But now it's not. It's two halves. So we've got a situation in which we charge up magnetically and then we discharge the magnetism. See, there's different things going on here. But when this is a toroidally magnetic pathway, a circular magnetic pathway, this coil up here, for all intents and purposes, let's say could be considered the primary of a transformer situation, and this is the secondary. In other words, they would have that kind of feedback to each other, although here it's bidirectional, it's not one way, so you really can't call, strictly speaking, one a primary and the other the secondary. They take turns, or, you know. But that would explain my use of simple transformers here with very strange coupling coefficients and inductance pairings in each of these two cases. Because this is a very simple circuit. It's just two transformers, two loads, and a clock representing the piston reciprocating action functioning at 100 hertz, which is not very fast. Now, if I'm not mistaken, I think Thomas Comerford Martin said 80 hertz, but William Line says differently. He says because the piston only has to move 1/16 of an inch, you can get very high frequencies. But he admitted to me in an email that he's speculating, you know, he doesn't know. He knows certain things, but a lot he has to speculate. So maybe it doesn't reciprocate much faster than 100 hertz, you know, because that's what I got going here. Look at this. This is 100 cycles per second. Duty cycle 50% because it's, you know, nothing, it's nothing out of the ordinary. Now the square wave is just the clock generating the pulse to represent what this is going through here. You know, in as much as certain things are turning on, turning off, I'm assuming in a strict sense, I'm assuming in the context of this simulation, you know, trying to simulate what he did. So this simulation may not be that far off, and it's really simplistic. It doesn't get any simpler, but that's because I've overly simplified the piston and the compressed air. I've literally taken that all of that out. But, you know, the brass in the middle here, if that's brass, and the aluminum rods underneath the H coils, and the fact that these are counter-wound, they might be joined in series, you know, all of that has to be taken into consideration. But I think that's my best guess, that this really, in other words, I'm not saying anything new in a sense, but I am in the sense that I'm trying to defend this simulation because, you know, in the past I would look at it and think, oh, this is ridiculous. Who can build this? How would you build it? Well, Thomas Comerford Martin and William Line also, but Thomas Comerford Martin actually more so because he's got a diagram. And William Line did take his treatise out of Thomas Comerford Martin to some degree, although he has extra sources of information to add to it. But, you know, he does refer to it, and that's why I finally decided to go and read Thomas myself to see what William Line is referring to. So it all comes back to Thomas, and everything else is extra. And this diagram is extremely important, and I tried to make an animated GIF out of it because I was trying to understand how the airflow works and why is it a regular periodicity to the reciprocating action going on here. How can that be? So once I went through it, I figured out and understood why. But in the case of the simulation, all that complexity is removed because we have a simple clock and some analog switches flipping back and forth. And that's at 100 cycles per second. That's why my time step can be so high at 200 microseconds, because they're not flipping that fast. And you can see they kind of get stuck once in a while. It's not even... Actually, no, they're not stuck. It's the simulation that gets stuck. It's jerky because I'm going too fast, so I have to slow down to... You know, it's still getting stuck. Yeah, it's still getting stuck. It's probably because I'm screencasting here. So anyway, regardless, so in the real world, they wouldn't get stuck. Don't assume that that's a property that's required. So this is how I go about defending this simulation. That this transformer is the H coils, and despite a coupling coefficient of 100, excuse me, no, not 100,000, 100 million. A coupling coefficient of 100 million. The inductive value is very low. In this simulation, it's 1 picohenry per coil. While in the M coils, we have a ridiculous inductive value of 100... let's see, what is that? Wait a minute, let's leave that there. Oh yeah, this will work. Okay, so exa, oh my god, 100,000 million, billion, trillion, quadrillion, pentillion. Okay, 100 pentillion henries, which obviously is not going on in these M coils, right? But, hey, for the sake of the simulation, I have to overcompensate. And the henries on these H coils down here, on these H coils, 1 picohenry? Maybe not. Coupling coefficient of 100 million? I don't think so. But you have to do things extreme undergoing in this simulation because Simulators are not designed to generate over unity. They're just designed to generate entropic, diminishment-oriented circuits strictly conforming to either AC output or DC output, not surges, certainly not spikes, unidirectional DC impulses, certainly not oscillating unidirectional DC impulses. So, that's the limitation of the software, but it's the interpretation of the simulation that's crucial to juxtapose or translate, be able to translate between the simulation and the real world. How would you go about building this? And so since I set about, in a very intuitive sense, to try to figure out how do I simulate this, I may not be that far off. This might be the best and simplest and most elegant way to simulate it. Notice I only used a 1-volt battery source, a DC battery source, to start this thing going. And then I can just make it climb to whatever value I want it to go. Now, I can't get it to change because the henries are too high, forcing me not to change. But if I reduce it to 100 kilohenries, there it goes. It wants to move upwards, see? Let's wait and let it go to mega values. Okay, and then we stop it and put this back on ETA. Is it ETA or EXA? EXA, right here, EXA, capital E. So we go to capital E. Let's see what it reduces to now. It should be higher than what it was before. Probably in the kilo range. Yep, there it is, kilo range. So that's 300 kiloamps plus 360 kiloamps, 260 kilovolts. So, that kind of proportionality is perfect for an electric car, and that's because the resistor I have alongside the inductor is so low, which may not be very practical. It may be higher than that, the resistance of a 1 Henry coil, so then your voltage will be higher rather than at this level. But anyway, that was the point of this video. The purpose of it is to try to defend the simulation, that it is realistic, it is buildable, provided we simply do what Thomas Comerford Martin and William Loyne has told us, and don't try to do it any differently. It will work. And this simulation is, I think, a pretty darn good approximation of what to expect, that it will work. Now, notice this is a DC output. That means in the electro U-boats they were using, see? William Loyne said that the device was simply used to recharge the batteries, while the batteries powered the DC motor that was turning the propeller at the back end of the electro U-boat. So it is a DC-oriented output system. It's not an AC-oriented output system. And we're not even powering a load, we're simply recharging batteries. So, I have a lot of circuits, and my intuition is that this is probably the most likely one that actually works. Now, I have a link to a web page that has various circuits that will work both in my realistic simulator, so-called, as well as Paul Falstad's version. And then I have yellow versions that are highlighted here, and one of them that's highlighted yellow is Tesla's special generator in an EV situation. The very same thing we've been staring at now. So, my intuition is that this is probably, of all the circuits I've done, this is probably the closest to something that's actually going to work. Now, I don't know. There may be a few others that I've come up with that actually do work in the sense that they're buildable. But this one I feel I already sense is buildable. You know, the other one that's a candidate in my book are the House of Mirrors circuits. These are superb, you know. Um, it's just, you start it up with a lawnmower, a lawnmower ignition coil, because an auto ignition coil would be the wrong value. And whoops, I'm using the wrong simulator. Sorry. So we go to a different simulator. Yeah, see, now that's the issue. Tesla special generator will work equally well in both simulators and put out the exact same output. But when we use just about any other simulated circuit, that's not the case. You'll get different answers. So here we have an output, and it's fairly constant, like Tesla special generator, and the only reason why the voltage is so weird is because, that was it. You had to super cool these coils, and then if you want to run it at normal room temperature, then you got to bring it down and change the resistance here to, what is it? 600 milliohms from the 1 microohm. So we changed to 600 milliohms. And restart the simulation, and now we get the voltage of whoops, I failed to change this one. What happened? There. So now we get the 145 volts and the 240 amps. Very similar to Tesla special generator output, but look what we had to do. We had to super cool the coils. You don't have to do that in Tesla special generator. So, by the way, the shortcut to this is is.gd/coolmag. And this only works in Paul Falstad simulator. It does not work in my realistic simulator. But the Tesla special generator simulation works in both and puts out the exact same result. It's amazing. And that's why I think this has the most promising virtue of being realizable. And so we just study Thomas Comerford Martin and William Line and go from there.